So let's start the last talk of today's afternoon session. So it's my pleasure to introduce Professor Fuchino for the chairman of the third speaker. Please.
Thank you. So I'm very glad that I may share the next and the last talk of the session. And the speaker is Professor Dr. Keita Yokoyama of Tohoku University. Dr. Yokoyama's main research field is so-called reverse mathematics, which is one of the major research subjects in mathematical logic. The reverse mathematics, very strange naming, was created in 1970s as a program which aims to reverse engineer, so to say, the axiomatic framework out of each of the prominent mathematical theorems like Cauchy-Peano existence theorem or Altsela-Ascoli's theorem and many other such theorems. So it appears that in many cases these theorems decide uniquely the axiomatic framework which they need. So that's the main subject of the field, but now there are many other subjects as well. And in Japan, a research group of this field of mathematics was founded by Professor Kazuyuki Tanaka, also of Tohoku University, in 1980s. And actually, Professor Tanaka is also a former thesis advisor of Dr. Yokoyama. So Dr. Yokoyama is now going to give an overview of this research field, including his own recent results, I think, under the title Reverse Mathematics from Multiple Points of View. So please.
Okay. So thank you very much for introduction. And I'll try to express my gratitude for organizers for giving me an opportunity in such a great occasion to talk about my research. So today I'll try to give a kind of a survey of my studies in the field of reverse mathematics. Okay, I'll try to start. So, I'll try to start the talk from the so-called Hilbert reductionism program in 1920s. It's a kind of an old program in Foundations of Mathematics, whose aim is to find a good axiomatic system T for the entire mathematics, and then for the safety of mathematics, prove the consistency of T by a finitistic method. Here, the finitistic method means that something like a symbolic calculation. But, well, this program actually failed because of the famous Gödel's incompleteness theorem in 1930, which states that, okay, if T is a consistent, well, recursive axiomatic system containing just basic natural number theory, then already the consistency of T is not provable from T. So of course it's impossible to prove the consistency of T by just finitistic method. But on the other hand, okay, Gödel's theorem, in a sense, suggests that the axiomatic systems form a hierarchy, meaning that, okay, well, to prove the consistency of some system, you need a stronger axiomatic system, meaning that it suggests a hierarchy of systems, and actually there is like this. Well, you don't need to worry about what are these, but probably the most famous axiomatic system is called ZFC for the axiomatic system for set theory, within which one can do formalize most kind of mathematics nowadays. And yes, but then, well, when you develop a particular area of mathematics, then now natural question arises that what axioms are essentially needed essentially required to do something you want? Well, because there's a hierarchy. Well, maybe at some level you can prove your theorem, for example, and that's I would say the start point of the reverse mathematics. And well, the reverse mathematics nowadays sometimes it is called Friedman-Simpson program, and then it is initiated from by the Friedman's theme in 1970s, saying that very often, if a mathematical theorem tau is proved from the right axiomatic systems axioms, then very often, well, tau is equivalent to those axioms over some weaker system in which itself is not provable, meaning that, well, indeed, very often tau implies axiom, so-called reverse direction, meaning that, well, which can verify that, well, those axioms are exactly needed to prove such statement. So with this idea, we want to classify mathematical theorems and saying that which is stronger, which is weaker. And here, well, so for this purpose, it's better to formalize mathematics in a possibly weak enough axiomatic system. And then here, we try to rebuild mathematics over the axiomatic systems for natural numbers and a set of natural numbers, which can be considered as a very, very, very weak fragment of set theory indeed. And the axioms is something like, well, just the natural numbers. The structure of natural number is just a discrete order of semi-ring, and then mathematical induction on n is available. And also we will consider so-called comprehension axiom of the form something like this. So for given a statement phi, well, okay, there's some set such that n is a member of S even only if phi of n holds. So just the usual comprehension. And then one can consider the complexity of the comprehension axiom by considering the complexity of this formula. Well, complexity means that we usually focus on the number of quantifiers appeared in P. But actually, indeed, the number of alternation of quantifiers, that's the essential part. But yeah, we will focus on that kind of thing. And now, okay, here, we try to focus on so-called big five systems. You don't worry about the real contents of these axiomatic systems, but the base theory is called RCA0, which consists of, okay, the n is a discrete order semi-ring and some restricted induction, well, actually induction for existential formulas, and then comprehension for so-called computable sets. Well, the computable set means that, well, vague idea is that a set computed from some concrete computer program, whether a member is in or out can be judged by some fixed computer program. That's the idea. Of course, the computer here means just the ideal computer. And then to consider stronger systems, we will add some axiom, comprehension axioms indeed. But well, okay, so for the second level, we would add, well, this axiom corresponds to in some sense, the covering compactness of closed unit interval. And the third one is obtained from adding some kind of axiom corresponds to the sequential compactness of closed unit interval. And with fourth one, well, the axiom is called arithmetical transfinite recursion, which provides some transfinite method. Well, some basic transfinite methods are available now in the fourth system. And if you do some more set theoretic construction, then the fifth system appears, called pi1 CA0. But, well, in this talk, you don't worry about the contents of each axiomatic system, but just consider as a classification. So from level 1 to level 5, and then you can do more mathematics more in a richer way, I would say. So using stronger compactness or using transfinite methods and so on. And it's known that by comparing with these systems, a lot of mathematical theorems can be classified, saying that, okay, this theorem is level 5 or level 4 or something like that. And well, a lot of those kind of results are found and also appear in kind of so-called subsystems of second-order arithmetic by Steve Simpson. It's a Bible of this field, the book, textbook of this field. And yes. And okay, so here just a brief idea of how to classify theorems. So for example, well, Banach's fixed point theorem for contraction mapping on, let's say, cross unit cube. Of course, given a contraction mapping on a cross unit cube, then it has a fixed point. And actually, the fixed point, unique fixed point, is actually computable in a sense, meaning that starting from any point and then calculate f of z and f of f of z and f of f of f of z and so on, then converges. And it actually, with a decent convergence rate, which can be computable from some computer program. And that idea can be formalized within this weak fragment of set theory. And so one can say that the Banach's fixed point theorem is provable within RC0, which means that it's a level 1 theorem in this context. While if you consider Brouwer's fixed point theorem on the cross unit cube, then, okay, now it's a continuous mapping. So in such a case, there's no computable way to find a fixed point. And actually, one can prove that there is no computable way, indeed. And that idea provides that the Brouwer's fixed point theorem is level 2. But if you have coupling compactness of cross unit cube, then now you can prove it. That's the idea. And if you go higher, like consider stronger fixed point theorem, like Calisti-Kirch's fixed point theorem, saying that, okay, on a complete metric space HD, given a positive, lower semi-continuous positive function psi, so-called potential, and then given any function f on this space, well, if the distance between h and f of x is always smaller than the difference of potential of those 2 points, well, with this situation, if you apply f, then you will lose some potential in a sense. Then f has a fixed point. And the proof is still very similar to the proof of Banach's fixed point theorem, starting from any point h0 and then consider this type of ordinal length sequence. So if alpha is a successor ordinal, alpha is some beta plus 1, then just h alpha is defined as f of h beta. And if it is a limit ordinal, then consider just the topological limit in the usual sense in this metric space. Then, well, actually, x omega 1, where omega 1 is the first uncountable ordinal, x omega 1 has to be the fixed point of f because there's no infinite, omega 1 length decreasing sequence of real numbers. So that's the idea. And indeed, one can prove that this is kind of a transfinite computation, but such transfinite computation is essentially needed to prove this theorem, which means that the Calisti-Kirch fixed point theorem is at least above the level 4. And in a similar way, one can classify many theorems. Here's just an example. And like the intermediate value theorems or the Banach's fixed point theorem, those things are actually proved in a computable way. And so so these theorems are, I would say, live in the level 1. All these are provable within the weakest base theory. While all of these are equivalent to the level 2 axiomatic system. Well, so it is. So they are provable within the level 2 system called WKL0. And actually, it is equivalent. They are equivalent. So like Brouwer's fixed point theorem or Cauchy-Peano's theorem for ordinary differential equations, or like the Jordan curve theorem, they essentially require the coupling compactness of closed unit interval, and actually it's equivalent in a sense. While the level 3 is examples are the following, like Alzella-Ascoli's theorem, or while the Riemann mapping theorem, actually the famous consequence of Alzella-Ascoli's theorem, all of these things are provable within the third system and actually equivalent, meaning that it essentially requires sequential compactness of cross-unit interval. So here, actually, I didn't mention, but the covering compactness and sequential compactness of cross-unit interval is not, well, the proof of the equivalence of those already requires some stronger axiom, meaning that they are different and one can separate level 2 and level 3. So yeah, I haven't mentioned that, but that's the idea. And then for the level 4, well, you can use transfinite argument, means that, for example, any two countable well-ordered integers are comparable, as famous theorem of well-ordered. And this is equivalent to the level 4 system. Or like if you want to deal with like Borel sets, then very often those type of properties equivalent to the level 4 system, for example, like this. And as I mentioned, Caliste's fixed point theorem is stronger than this system. And the level 5 is called Parent's comprehension. Now the theorems like this is more often appear in the setting of set theory. The first one is Cantor-Benedictson theorem, states that while any closed set in Euclidean space can be separated into a countable set and a perfect set. So perfect means that there's no isolated point. So that's the Cantor-Benedictson theorem, and that is equivalent to the level 5 system. So another question is that, well, these axioms, these kind of stronger type of axioms are only needed for more like abstract or set theoretic settings or not. I mean, I actually thought that, okay, well, to do some more abstract math, we need stronger axiom. But if you do just a, well, I don't mean that they are easy, but if you want to just work on, for example, Euclidean space, then usually the weaker axiomatic system is just enough, I thought. But recently, I actually find a kind of a counterexample to that intuition. So that's here, Ekran's variational principle. Probably many of you already know the statement, but I will try to say it. But if HD is a complete metric space and then F is a positive function, let's say that the point H is said to be a shoot minimum or critical point. If, well, this holds, means that, okay, it's like a strict minimum, but we will add this one. So compared to the distance function, it is kind of a minimum. So that's called shoot minimum. And Ekran's theorem says that, well, on any complete metric space and any lower semi-continuous, positive lower semi-continuous function, there is a shoot minimum. And that statement actually equivalent to Parent comprehension of the level 5 theorem. And indeed, if you restrict the theorem to just the space of continuous functions on cross-unit interval, still it requires level 5 system. That's the idea. And, well, Ekran's theorem is often used in optimization problems or PDE. So maybe there is a kind of a concrete, very specific concrete optimization problem or PDE which already requires the level 5 system. Maybe. That's open. But that might happen. So on the other hand, of course, many theorems are not easily to be classified. So there are many exceptions as well. Like these theorems, like Hilbert's basis theorem or monotone convergence theorem, those things are kind of exceptions. And they are not equivalent to any of big 5 systems. So indeed, in the recent study of reverse mathematics, well, more people are interested in finding this kind of exceptions. And nowadays, so many independent combinatorial, especially combinatorial principles, below the level 3. Like this picture, I would try to say. So this is an abstract picture of a so-called reverse mathematics. You would find this picture in this web page, and actually I thought the owner of this web page drew this picture, but actually he told me that his mother painted this picture. But anyway, the real one is like this. So this is the real diagram. Well, we may see the inside in there. And then there are so many independent statements, and actually each express the relation between them. So this is stronger than this one, and this is stronger than this one, and so on. So it's indeed a huge picture. Also, oh. So like this complicated picture. So here's the observation. So many theorems, like in undergraduate math, roughly speaking, are classified into the first 3 levels. That's, well, just by experiments, but yeah, very often that happens. On the other hand, of course, there are also many exceptions. And especially very often, the various combinatorial type principles provide independent statements. And on the other hand, independent statement meaning that it's not equivalent to a given axiomatic system means that those may be considered also as axiom, in a sense. But then the question arises, how can we calibrate various types of axioms or principles? Well, they are not linearly ordered. So I would say we need some newer types of, or I mean, not new, but some multi-dimensional measures, or like invariants, to say that which is stronger or which is weaker. So here the idea of multiple viewpoints. So the first one is actually computability or complexity strengths, which already I mentioned, like a focus on the complexity of a comprehension required and measured by the complexity of a formula. While the second one is a bit different type of strength, the so-called proof-theoretic strengths. And in the next slide, I will explain the detail. But the idea is measured by the hierarchy of so-called fast-growing functions on natural numbers. And meaning that bound the search range over for a statement some statement on natural numbers, something like for any natural number x, there's y, such that something holds. Then okay, we'll try to bound the search range of this y, and how fast-growing function is enough to capture the range, search range. We'll try to classify theorems by that viewpoint. And the third one is called constructivity. It is well, the research of this type is often called constructive reverse mathematics, or also the so-called study of viral degrees leads to this direction in a sense. Well, so yeah, today I cannot talk about this much because to calibrate this type of strengths, we needed some kind of different frameworks are needed. So I don't want to talk about, I won't talk about much about it. But the idea is, well, here, like what kind of non-constructive principles are needed? And non-constructive means like proof by contradiction. So to prove something exists, then very often we use the proof by contradiction, that saying that, okay, assume that for any x, well, no x satisfies phi, and then reaches the contradiction. That means, okay, there's something. But of course, that way of proving won't provide what this x is. So it is often called its non-constructive proof. And here, okay, we try to focus. So I won't say that non-constructive proof is bad, but just here we want to focus on the use of those type of non-constructive principle, and focus on that, and then you can classify which is stronger, which is weaker. And indeed, for example, well, as I mentioned, so with this with this measure, one can say that Banach's fixed point theorem is strictly weaker than Brouwer's fixed point theorem. And the second one provides something like the fundamental theorem algebra. It's weaker than Hilbert's basis theorem. And the graph minor theorem, it's a theorem in graph theory. Theorem in graph theory. This is actually extremely strong in the sense of these strengths. I will see it in the slide later. But yes. And then here, well, a very vague idea of how to calibrate the proof theoretic strength. So that for that, we will consider the hierarchy of fast-growing functions, so-called fast-growing functions. And so the idea is, okay, f0 of x is just x plus 1, and f n plus 1 of x means that you will apply f sub n x many times. And the result is the fn plus 1x. So starting from x plus 1, then you will get f1 is 2 times x, and f2 is x times 2 to the x minus 1. So it's almost an exponential function. And the third one is actually almost a Taubel function, 2 to the 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 x many times. And f4, f5, and you will consider this kind of thing. And then if you reach the limit ordinal, then we'll consider diagonalization of those things. So f omega of x means that f sub x of x. It's there. So it grows faster than any of these things. And this hierarchy can be compared with the hierarchy of ordinals. Well, I won't say anything about what these ordinals are. But very roughly speaking, well, okay, when you consider a statement of natural number of this sort, for any h that's y, theta xy, well, this is bounded by some fast-growing function. F sub alpha almost means, well, not exactly given, but almost means that, well, this statement is provable from some reasonable base theory plus well-orderedness of corresponding ordinal. So in a sense, hierarchy of fast-growing functions and hierarchy of ordinals are comparable, and well, essentially the same thing. And this actually corresponds to the so-called strength of consistency, which we have seen in the first slide. And also, the strength corresponds to the hierarchy of induction. So the induction strength, how much strong mathematical induction is needed. This measure also express that kind of strength. And with using computability theoretic strengths and proof theoretic strengths, now all of these kind of exceptions can be seen in a better way. Not just saying that they are independent, but actually where they are. So for example, the Riemann integrability is, okay, computability theoretic strength is non-trivial but below level 2. And the proof theoretic strength is weak. While like the Hilbert basis theorem has no computability theoretic strength, but the proof theoretic strength is non-trivially strong. And actually it implies a consistency of level 1 system, meaning that never be proved from the level 1 system because of the Gödel's incompleteness theorem. And like the monotone convergence theorem, in the sense of computability, it's independent from level 2, but actually it's still below level 3. And the proof theoretic strength is weak, fairly weak, but little stronger than this one, for example. And Kruskal theorem or graph minor theorem is theorems in graph theory, and they are known to be very strong in the sense of proof theoretic strength, while they are actually theorems about finite objects, meaning that there's almost no set theoretic comprehension is needed. So the computability theoretic strengths are both are very weak, while the proof theoretic strengths are very strong. Very strong means that actually they are proving the consistency of the level 5 system, meaning really powerful. And here, Ramsey's theorem for pairs appears here. Is actually a very interesting topic, and the later of this talk, I'll try to just focus on Ramsey's theorem. So the Ramsey's theorem here means that actually infinite Ramsey's theorem in the setting of graph theory. So meaning that given a k-coloring of a edges of complete infinite graph. Complete graph means, so infinite complete graph means that there's infinitely many points, and each 2 point between any of each 2 point, any 2 points has an edge. So that's the infinite complete graph. And if you color each edge by k colors, then there must be an infinite monochromatic complete subgraph. Monochromatic means that the color appear in this subgraph, complete subgraph, it's just one color, one fixed color appears in the subgraph. It's a famous graph theory statement. And the strength of Lambda's theorem, so it's actually a two-dimensional Lambda's theorem, but the strength of Lambda's theorem is one of the main interests in the study of Lipper's mathematics for a long time. And indeed, so the computability theoretic strength is, well, it's a very interesting topic. And it is known that it doesn't always have a computable solution, but always has a solution with lower complexity in many sense. And there are a lot of studies in this direction from 1970s, and still there are new papers, new theorems around here. And a book essentially just devoted to the study of this type of question by Dean Hirschfeld. It's a very, very, very nice book, and I like it. And strength in the sense of constructivity is fairly strong, I would say, because so Lambda's theorem, this is two-dimensional case, but the one-dimensional case is if you just color the not edge, but just vertices, then that's simpler version, and that's just the pigeonhole principle essentially. But pigeonhole principle is, in a sense, it's a very, very strong form of excluded middle. Well, maybe not very strong, but it's a kind of a strong form of excluded middle. Because, okay, if you just consider pigeonhole principles with just two pigeonholes, meaning that, okay, there are infinitely many pigeons and 2 holes, and then one of them should be infinite. That's kind of excluded middle. And the proof-theoretic strength of Lambda's theorem was a long-standing open question and recently solved. That's this. So the proof-theoretic strength of infinite Lambda's theorem, well, if you just consider 2 colorings, then its proof-theoretic strength is characterized by the hierarchy of fast-growing functions up to the finite level. And if you consider more colors to say that the infinite Lambda's theorem holds for any finite number of colors, meaning that the one level up, I would say that, but still the fast-growing function a bit bigger ordinals, I would say. And the idea of the proof is that, in a sense, it's interesting because it contains some, well, it comes from so-called old important famous topic in the study of mathematical logic, so-called Price-Harrington principle. The Price-Harrington principle is it's known to be the kind of first example which is not provable from the so-called famous arithmetic system called Peano arithmetic. Peano arithmetic just consists of a axiom for ordered semi-linear on natural numbers plus mathematical induction. So the Price-Harrington principle, it's a variant of a finite Ramsey's theorem, but it's not provable from just simple mathematical induction. And then the proof that why this is independent is based on the idea of this correspondence. Well, this is just very vague description, but the structure with finite lambda theorem and the structure with infinite lambda theorem has some correspondence from the view with the idea of something like non-standard analysis, meaning that, okay, well, if you consider a non-standard model of the finite lambda theorem, then, well, okay, in such a model, you would consider a lambda theorem holds just in the finite sense. But the structure itself is like like for non-standard analysis, you may find something like infinitely large object or infinitely small object. And in that world, okay, even if you believe that finite lambda theorem holds in that hyperfinite structure, well, you may cut off from outside, you may cut off something like an internal infinite structure from it. And that structure must satisfy some version of infinite lambda theorem. So there's such correspondence. And indeed, finite lambda theorem itself has a nice correspondence with the hierarchy of fast-growing functions. And so that corresponds to the any kind of consequence of infinite lambda theorem on natural numbers. So I would say this is a very beautiful structure, and I wrote about it in the ICM proceedings volume. So if you're interested in, please see that. And another observation is that infinite lambda theorem itself is in a sense it's a meaningful axiom for infinity, or indeed countable infinity here. But and the proof theoretic strength described here is actually fairly weak, meaning that the infinite lambda theorem is a good axiom without adding extra proof theoretic strength. That can be considered as sometimes considered as a partial realization, well, actually tiny partial realization, but the partial realization of Hilbert's program. So the original Hilbert's program in the first slide, want to develop, wider range of mathematics in a hopefully weaker proof theoretic strength. That's the idea of Hilbert's program. So it can be considered as a partial realization of that. So you can add richer infinity axiom without changing the consistency of proof theoretic strength. So the consistency strength, even if you add infinite lambda theorem, you don't need to worry about the increase of the hardness of proving consistency, but you can add extra axiom. So it can be considered as a partial realization. And indeed, if you formalize that kind of idea, one may get some applications to like theoretical computer science, especially like a analysis of termination in the context of like a program termination. And related discussions around here, it's appeared in some kind of a general public article in Quantum magazine in 2016. There's discussions by several specialists in this field. And anyway, with those analysis, what we had is that now we have some better calibration of the strengths of lambda theorem. I would say the three-dimensional calibration in a sense. So that if you consider like the one-dimensional lambda theorem or like three-dimensional lambda theorem or above, it is known that they form a hierarchy like this. So here, RD and K means that the lambda itself for n tuples and K colors. It forms a hierarchy. And then if you focus on the computability theoretic strengths, Well, one would say that the first two things are the same, and actually it's trivial strengths. And then the second two things are the same. And if you consider triples, it's stronger. And if you consider quadruples, actually it's stronger than this one, and so on. But if you consider proof-theoretic strengths, and then first three things are the same. And if you add more colors, then go up. And then if you consider triples, then go higher, and so on. And if you consider strengths in the sense of constructivity, then the first level already have some non-trivial strengths. And the second level is stronger than that. And third level, okay, I would say that in some sense it's stronger, but it depends on the formalization. And today I didn't formalize the idea to talk about this strength much, so I can't say any more. But well, we can calibrate the strength of Ramsey cell from the viewpoint of constructivity as well. Okay, so now the for my future topics, I would say not for the. I don't mean that these are the questions for our field, but just for myself. But anyway, so my general research motivation is something like it's seeking for a better way to calibrate or classify or perhaps understand mathematical theorems. And then in the setting of debate mathematics, well, I think these questions are interesting. Like can we find more like useful axioms for like combinatorics, for example, from combinatorics, or how the different types of measures are related. So here, today we thought three types of measures, and then how they are related. And can we consider some other types of measures? Or like the more naive question is that more difficult math theorems require stronger axioms. Here, difficult means the kind of real difficulty for mathematicians, not just about the sense of axiomatic mathematical logic, in the sense of mathematical logic, but just for difficulty for mathematicians. That's the idea. And then, well, there are several ongoing programs for each of these questions. Like for the first one, well, like so-called Heinemann theorem and Gauer's theorem can be a good candidate as a new axioms in a sense, and also if we consider the new type of measure, probably the length of proof is a kind of a natural thing, and actually it in a sense it works in a sense. And this is indeed a kind of an ultimate question, but like can we verify that the difficult problems, like the long-standing open problems, like a millennium problem, for example, can we say that they are indeed difficult in the sense of mathematical logic? That's probably the ultimate question, and I don't know whether I can reach those type of questions or not, but yeah, that's probably a good goal. And as a final word, I've tried to quote one sentence from the Richard Schwartz survey article. So I urge you to come on in and join the fun. So well, okay, I would say, well, so if you're interested in, I mean, so indeed, the non-logician's knowledge is very, very helpful to study this kind of study, this type of research. I mean, because, well, logician's knowledge is quite limited in many cases, while we want to know the strengths of more difficult theorem. So that's very helpful. Okay, that's all. Thank you very much. And here are the references. That's all. Thank you.
So thank you very much for your very, very much inspiring talk. Are there any questions in the audience? Or For those in the Zoom space, if you have any questions, please raise your hands. Are there any questions? No questions again? Are there any stupid questions? No? Please.
So, may I ask a very naive question?
Sure.
And I'm a PD. And for instance, I have the impression that the infinite dimensional case, we need more higher level action. And can you judge, for instance, mountain path lemma or some maximum principle for harmonic function? This is proved by, for instance, maximum principle is proved by contradiction. And can you judge which level of these famous theorems?
Yeah, well, so for harmonic functions, actually, there's some results, and some of them still lives in the second level because, okay, where it is. So like here, for the harmonic function or holomorphic functions, the Cauchy integral theorem is available in the second level. And so with that idea, some of them is provable. But I don't know. I mean, it's actually very hard to say before calibrating the exact strength by hand. But maybe we need some kind of a nicer framework to guess the strength in an easier way, just from the statement, for example. But that's probably the future work. I don't know. I can't do that now. Yeah, thank you.
Okay. Any other questions? So in that case, I have actually several questions. So first question I thought was hearing like the previous question, how about Fermat's theorem?
Yeah.
Where was it to put in this picture?
I don't know. I don't know. I mean, well, the problem here is that to calibrate the theorem, I need to know its proof very, very well, and that can be a very high hurdle sometimes to know the exact strength of its theorem. So I've actually heard from some of my collaborators that it should be below the level 3, but I mean, I don't know whether he analyzed the real proof carefully or just guessing. So I can't say much more about it, but yes. Yeah, that's difficult indeed.
Another question would be about this zoo of reverse mathematical world.
Yes.
So you mentioned that you can introduce 3 different type of
measures.
And so do you think that you can bring some more order in the zoo, or is the zoo remain just a chaos?
Well, can be understood better because, well, if you just focus on process, so these kind of measures can be considered as an invariance, for example. And then, okay, well, in this zoo, in this chaotic zoo, actually, if you consider just proof theoretic strengths, then the shape is much simpler. And it's almost linear indeed. And categorized to, in this situation, probably 5 or 6 levels, I would say. So can be helpful to understand chaotic zoo situation in much better way, I think.
So, any other question? So if there's no other question, perhaps I have still some other questions, but I'll ask you after. So thanks the speaker for the nice talk. Thank you very much.
Thank you very much.